Page 42, let's take a look at number 57, right? And one of the things that was mentioned on Friday was having more practice problems, so let's just do a few. We will have another quiz on Thursday. Since you've doubled, essentially had your points, the way your points worked, you actually had a full test between the Thursday quiz and then the homework. This Thursday's a quiz. Okay, so we're just trying to keep the correct number of points since we had that extra points over the weekend. Then we'll just go with the quiz on Thursday, unless you really want a test. I didn't think so. All right, so it says a person jumps from 4-story windows 15 meters above a firefighter safety net. The survivor stretches the net 1 meter before coming to rest. So you have one of these scenarios where they have this fireman's net, and the person jumps off. And the way it looks in the book, right? You've got this person jumping down, and then you have this thing here where this is 1 meter, like that. Okay, and this total height is again above the fireman's net. So from here to here is 15 meters, right? Now, what piece of information was not given that is assumed to always be true when a falling object? Acceleration is negative 9.8 meters per second squared. Okay? Now, let's take a look at the thing. It says, what's the average deceleration experienced by the survivor when she was slowed to rest by the net? Okay, so deceleration, which means there has to be in this area. So what I'm going to do, I'm going to draw this a little bigger. So here's the net, right? So from here to here, there had to be an initial velocity here, and there has to be a final velocity here so that I can then get the deceleration that I'm looking for in the problem. Does that make sense? Okay? Final velocity, of course, is 0 because they're in the bottom of the net. The problem is, how do I find that initial velocity? Yes, ma'am?
So is the reason that you know that your like VI and VF is centered around the net and not the entire thing is because it's asking for the deceleration when you're slowed by the net?
That is absolutely correct. So the whole problem is questioning the net. But there's other information that's going to help us inform that, right? So how do we get an initial velocity at the net? She had to be moving, right? Yeah. Otherwise, it's 0, and that doesn't make any sense. So what do you think's happening here?
Wouldn't it be your final velocity jumping out?
It's the final velocity of the jump is actually the initial velocity of the deceleration. Okay. Hi, Brenna. I didn't know you were back. Glad to have you back. Did you survive? Yeah, I know. It's tough for them. I can't imagine being at home trying to watch the silly things that I do. All right, so this final velocity of the jump is the initial velocity of the net. Is everybody good with that? Okay, so then I need to know if the initial velocity here is 0. We're assuming it doesn't tell us anything about the person jumps from a 4-story window. They're not going to jump up, right, out of the window, because then they'll be just going faster. They're probably just going to jump out and try to land in that net, right? So there's no velocity, final velocity. So what I have is initial and final acceleration and distance. So VF squared equals VI squared plus 2AS. Now this is for the jump. Everybody see? I'm trying to separate it into 2 pieces. We've got the jump and you have the net. Yes, ma'am.
I don't know if this question makes sense, but like I'm confused. Like sometimes like when you just use V, like if it's in the formula, it's like VT, or like how that differs from like when you use velocity.
That's a great question. V in VT is an average with no acceleration, right? SF equals SI plus VT The V is an average, and it's constant.
Okay, so you can't use that whenever it's like it jumps off because it's accelerating.
Bingo. You can't use that first of the kinematic equations if there's an acceleration. Okay? Or at least in that dimension. Like we're doing vertically, if something's falling, it's got an acceleration of 9.8. So we just solve this. Vf squared equals 0 plus 2 times negative 9.8 times 15, and then we'll get a final velocity. Anybody? 17 point. 17 point. Let's go do 17.2. And then this becomes in the net, right? This becomes that initial velocity. And that's why it's so important for you to keep your stuff separate, right? Many of you are keeping your information in very, very good order. Sometimes I don't leave enough space for you to work your problem. That's my fault. I will try to work on that so that you have more space. But some of you have been going to a second page and just been opening it up, and it's been very easy to find things that I need to grade because you've been keeping good track of your information. This is the key to the whole thing. Here's the original drawing. This jump, it becomes this in my drawing, and now I have my two pieces laid out. So I said, what's the average deceleration experienced by the survivor? So I'm going to, I've been given a distance of 1 meter from here to here, which is, you know, they're holding it like this. I don't know if you've ever seen firemen hold this. They literally hold the ring against their, right here on their body, because that's the strongest place, right in their shoulders straight down to their feet. They're not holding it like this because that's their arms. There's no way that their arms are as strong as this up here. Yes, ma'am?
So, when you found the final velocity for like the top of there to the net, are you just pretending like there's not enough there for right now?
But no, we're talking that that's the velocity right before they touch the net.
So why wouldn't you use 14 meters for your distance?
Because in the drawing, it says 15 meters above the net.
Okay.
Now, see what she did. She did the right thing. She's in there looking and going, wait a minute, 15 meters up, 1 meter net should be 14. That can be a trick, but in this case, it actually says 15 meters above the net. Okay? But that's good thought. Good thought. So we'll just go in here, final velocity equals initial velocity plus acceleration, or 2 times AS. Final velocity, these are squared, 0 equals 17.2 squared plus 2a times 1. So what's the acceleration at that point?
Negative 147.
Pardon?
Negative 147.
Negative 147 meters per second squared. Now, seems like a lot. So how do we get this into our world of understanding? We create G's. Now, it didn't ask you to do that, but if we were to create this as G-force, we'd take our 147 and divide it by what? 9.8, correct. So we'd be 15. So this is 15, a negative 15 G's. Now, to give you an idea, 15 G's is probably going to hurt. It's probably not going to damage anything unless you land incorrectly. If they land properly, which means they jump out and their feet come up like this, and they're landing with their rear end down, right? You're catching it on the rear end and on the big muscles, not trying to land on the net with your feet. That would hurt if you landed on your feet. So when you land out, you always land, you jump up, and you land on basically on your rear end. And then it takes all the energy away. Yeah.
How come it's negative 15 and not positive if you divide it negatively?
Here's deceleration.
This is deceleration. A G is 9.8.
Oh.
I'm not dividing it by the direction 9.8. I'm just dividing it by the number 9.8, which gives us G's. Great question. Everybody understand that? This is actually telling you the direction that's already there. So I divide it by 9.8, and I have negative 15 G's. Okay, that just gives you an idea. Roller coaster's 4 G's, right? Max 4 G's. and you can sustain 4 Gs for quite a long time. 15 is like, poof, and you're like, ugh. You okay? Yeah, I'll get it. Usually they just get right out. And they might hurt their back a little bit. They can get treated for that, but they're not dead from a fire. I mean, this is one of the things that that they use for years. And I don't know if you remember, but about 1880, there weren't any buildings taller than 4 stories. Period. And it's because they were made of wood. And when you build up, the wood on the bottom gets stressed too much. And then if you have to build the bottom out bigger to support a higher floors, then the first floor is all beams holding up the rest of the building. So 1880 to 1890, they started coming out with steel. And all of a sudden, you could go to 10 stories, and there was masonry. And they would, they'd face the building with, they started with masonry, and they would go up to about 10 stories. And it started having problems with the fire department. Ladders only went to 4 stories, and they built a 10-story building. Yeah, Molly, that outerwear is not appropriate. Yeah, I know nobody else catches it but me. It's the joy that I have during the day. It's the fun that I have all day long. So when you have 4-story buildings, that's all you've got. Somebody builds a 10-story. What's the fire department do? We got to get new ladders. We got to get new ladder trucks, and all of a sudden, high-rise elements become a problem. All right. So then they started putting in sprinkler systems within the buildings to assist that. And so we have sprinkler systems in here because that's code. Although a 2nd-story building, you could jump out the window if you had to. Now it hurt. You probably break a leg, but broken leg, live, die in a fire. Pretty easy, right?
I think that window would stop you. I don't think you.
I have several things I can throw through that window that will make that window disappear. Yeah, trust me. I see all those things on the wall. I can. All right. So, questions on that one. All right. So let's go to B. It says, what would you do to make it safer? That is, to generate a smaller deceleration. Would you stiffen or loosen the net?
Loosen the net.
You'd loosen the net. But at some point, don't you have a problem if you loosen the net too much?
You hit the ground.
You hit the ground. I know none of you have had this happen, but we got a trampoline when my kids were young. I didn't want a trampoline. I caved in and allowed the trampoline. We only had to go to the hospital once in the first day because I knew the kid. It's just the way trampolines are. And I was like, I don't want to take him to the hospital. Well, the head and the chin come together, and teeth and whatever. Anyway, so Dad, get on the trampoline. I'm like, yeah, I'll get on the trampoline. Bounce a little bit. Dad, try to bounce high. And I said, no, you don't understand. I'll hit the ground. And they're like, no, you won't. So I started bouncing, and I wasn't bouncing very hard, and I hit the ground. It's 4 feet off the ground. And it was in the middle, and I hit the ground. When I'm on my feet, I know it's going to happen because I'm bouncing it. Like, boom, there it is. And they're like, wow, you weigh a lot. Like, yeah, considering that you're like 6, and but that's one of the things that you have. If you loosen the net too much, you create a second problem. So be real careful when a question like that. You would loosen the net. If a guy's standing like this and 1 meter takes it down to here, you could loosen it maybe a little bit more and decrease you would decrease the deceleration by making this number bigger. Okay, now consider the same idea with a stuntman. Right? Stuntman, not 4th story. He jumps out of the 10th story window or off the roof. In real life, in a movie, there's not some guy standing there with one of these, and he's not catching 15 Gs because he's not going to do that very often, right? They're going to try to keep him at 8 or 9 Gs. So instead of this being a mere 15 meters here, right? If he's 10 stories up, this might be 30 meters. Now you're talking a whole different animal, but you know what they do down here? They put a pad, a huge pad with air in it, right? And what they initially did was they piled mattresses up or something like that, and they fall on the mattresses. Then they found out mattresses eventually wear out and you hit the ground. Pole vaulters, right? What pole vaulters do when they get themselves up and they flip over the bar and then they land on their back, right? And what ends up happening is that pad, it's about this thick. If the pad wears out, you hit the ground. And there are certain meets that we go to where there's an old pit. And they said, anybody here should jump over 15 feet? And they go, yeah. Says, you can't jump over 15 feet today because you go to 15 feet, you're going to hit the ground. I'm like, get a new pad. But they're like $10,000. That's why they don't get new pads. But you think about that, if you're jumping not from 15 feet, from 30 meters, which is almost 100 feet, okay? You're talking about a tremendously different velocity, a different deceleration. So what they end up doing is creating a pad, and they fill it with air. Now, you got to be careful. If you fill it with air, it just becomes a big bounce house without walls. And you go, dong, and you bounce off, and then you land on the asphalt, and then now you really got broken bones. And so what they do is they actually have flaps on the side, right, that are Velcroed on, and they inflate it, and the air that leaks out is really minimal. If you're familiar with a bounce house, right, some air gets out, but it's pretty tight. What they have is they have these flaps, and when something hits it, the flap goes like this. It opens up, and there's a big old hole, and air flows out really fast, and they have several of those. So when he lands, it goes, and it goes, and the guy gets off the pad, and they fill the next one up and says, do another take. So he runs back upstairs, and they jump off again. So what'd you do today? I jumped off about 100 feet. How big was the pad? Well, that could be a problem on a quiz on Thursday, right? How big's the pad? So what we would have to do is maybe take a look at this, and I'm going to leave all this up here. But if I said, what if he wanted to have a landing that was -9 Gs? Now he's jumping from 30 meters, so we'd have to work backwards. I'm jumping from 30 meters, I want -9 Gs. So I want to be 100 meters above the pad so I get the best camera view for the longest time. I need to be 30 meters above the pad. So how big's the pad? Well, we take a look at this. -9 Gs here, and that's going to impact how big this is, right? So my -9 Gs, I take the 9 times 9.8, and I get 88.2. That's going to be the acceleration I'm shooting for. Okay. I know it's 30 meters, so this instead of 15 is 30 meters, which changes my velocity, right? See where I'm going? I'm working from both sides toward the middle because I'm trying to find out what that number is. So you end up 2 times 9.8 times 30 equals, and you take a square root of it, so 24.24. So 24.24 meters per second. So he's doing about 60 miles an hour when he hits the ground, hits the pad. Yes, sir.
Could you walk through what you just did 24.24?
I took this 30 and stuck it in here instead of 15, because this was 15 meters and I doubled it. He's jumping off a 30 off a 30 meter building instead of 15. Okay? Everybody else good? Now I can plug this in here, and I can solve. If I know what A is, you see what's happened? I know what A is. I'm now solving for that. So I take my 24.24, I square it, divide it by 2 and divide it by 88.2, 3.3 meters. So my pad has to be 3.3 meters in depth. So I'm working at both sides. This is where it gets confusing because I'm trying to find something in the middle instead of something at the end. Yes, ma'am.
Where'd you get 24.2?
Right here. By taking this 30 and putting it in for distance right here instead of 15.
So that's what replaces the 17.
Right. So how fast is he going when he gets to the pad is 24.24. I plug that in over here, and I plug in the acceleration that I want. This -9 is easily survivable. In fact, fighter pilots are trained to handle 9 Gs. Okay? Actually, sustain 9 Gs. Stuntman, that's thump, blows the air out of your lungs, and then he gets up and gets off the pad. Absolutely fine. No problems involved. Okay? But you notice, the first time we did it, we were solving for this acceleration. The next time we did it, we changed the acceleration that we wanted, came back up in here with the new information, came at it from, so you're actually coming at it from both sides, which is a method, one of the methods that we need to learn how to do. Yes?
If we have a problem like that and like we have to do it both like 2 times, like if we get the first answer wrong and that makes us get everything else wrong, will you still give us?
Well, let me ask you a question. You've been in my class a year, almost a year and a half.
Right.
Do I get partial credit?
Yes.
There we go. All right? Cammy.
What was that question again?
Okay, here's what the question would look like. All right? And if you want to write down how the words would be in redoing this in red, it would be like this. A stuntman is jumping off a building and is 30 meters above the pad. He wants only 9 Gs of deceleration, which would be -9 here. How thick's the pad? Okay? That makes sense? Yes, ma'am. Yes. All right, other questions? Yes, ma'am, Mackenzie.
How come, so, I'm just confused, did you plug in -88.2 in the acceleration, or were you?
Yes, I plugged -88.2 there because instead of me getting a 15, I said I only want a -9.
Right.
So that means I multiply by 9.8. So going this way, I multiply by 9.8. Here, when I'm going this way, I'm dividing by 9.8.
Right, that makes sense. I'm just confused on how by plugging in -88.2.
That's the acceleration that the guy will experience.
So how did you get 3.3?
By plugging in 24 here, plugging in 88, and then solving for that. So that instead of being 1 is now 3.3. Right. You actually solve for the distance. In the original problem, you were given the distance. Now you're solving for the distance. Right? All right. So that's one idea. All right. Now let's take a look at the next problem, number 58. And number 58 is kind of unique. It says acceleration due to gravity on the moon is about 1/6 that of the Earth. If an object is thrown vertically upward to the moon, how many times higher will it go than on the Earth, assuming the same initial velocity? So let's work a problem on Earth and then go to the moon and see what it's like on the moon. So let's say the initial velocity is 22 meters per second. And the acceleration to gravity is -9.8 meters per second squared. And I'm trying to find how high it goes. Well, on Earth, the final velocity is going to be 0, right, when it gets to the top. So I'm just going to solve this, Vf squared, Vi squared, plus 2As. This is 0. This is 22 squared plus 2 times -9.8 times S. So this becomes -22 squared divided by -19.6 is the distance. Right? So just solving this normally for distance, this is what this is, and that would be 22 squared divided by 19.6, 24.7 meters. All right, so that's nothing new, right? That's pretty much, if I throw a ball 22 meters per second up in the air, it goes 24.7 meters into the air. Here's my gravity, and we're good to go. Yes, ma'am.
And so you just pick like a random number.
Yeah, I just picked a random number to create a scenario, a reasonable number, because that's less than 60 miles an hour, which there, you know, even in this room, there are people who can throw it that fast. If I had it at like 40 meters per second, that's like 90 miles an hour, right? I have hit baseballs off of guys who threw it 90 miles an hour, but those were rare. Playing in high school, it never happened. It only happened once in college, Elmer's College, last game. The guy was being recruited by the Dodgers, and we played a pretty good game against him. But he threw 90, 92 miles an hour. It was fast. And I can't imagine a guy throwing 100, which if you watch baseball, guys throw 100 miles an hour, it is like, I mean, just he lets go of it and all of a sudden the ball's in the catcher's mitt. I just don't have a clue how you hit something like that. All right? So this is our, now, pardon?
You don't, you just say good pitch.
Yeah, you just, or you try to bunt or something. All right, so what would change here if we're on the moon? So the same, everything's the same except the acceleration of gravity, right? So we would have the acceleration due to gravity as 9.8 divided by 6 because it's 1/6 the gravity on. So how would that change? That means this right here would, let me do that in a color here. Okay? So now, this number, instead of being negative 19.6, it would be 9.8 divided by 3. 3 so this number would be 3.27. And so you take 22 squared divided by 3.27, and it's 148 meters. Now, if you take this 148, divide it by 24.7, anybody got an idea what that number is going to be? 6. 6 times as high because the gravity is 6 times less. That makes sense? Just go 6 times as high because it's 6 times less gravity. Gravity's not slowing it down as fast by 6 times. So it goes 6 times as high. Right. Well, since we've gone through it in class. Yes, ma'am. Oh, you want to follow? Do you have a follow up on that? Okay.
So like since you know there's just like 6 times as much, you just multiply by 6. Like once you find like where it's
Right.
gonna be like on Earth.
Right. So if we went to Mars, it'd be divided by 3. Now, you're not expected to know that number. Okay? I would give you the number, the varying gravity. If you, by the way, if you were on Jupiter, it'd be 2.5 times the gravity. So gravity would be bigger on Jupiter, which means this would be, divide this by 2.5. It'd only be like 10 meters high. Because the gravity is so strong. Right? Yes, ma'am.
So if we didn't have that work and we just had it 6 times as tall, it would still be correct.
Yes. Here's the problem, though. If there's another problem. The question is, does it work to just divide or multiply by 6 on every type of problem that ever gets? But on this one, yes. Now that you've seen that. Yes.
So I might be completely off on this, and I know you said that you would give us like the differentiation and like gravity if we had a problem like this. But say we didn't know it, could you just use the same equation and plug S in and leave A like as the variable you're solving for and get that?
Yes. If I gave you this, if I gave you the distance, yeah, you could solve for A, and you could use that as a way to figure out what the gravity is on the moon.
Okay, but you couldn't use 24.7 because that would just give you negative 9.8.
Correct. Correct. Sir?
Are you giving the initial, or will we be giving the initial velocity?
Yes. Yeah. I'd have to give you enough information, so yeah, I'll probably give you that. All right. Now, here's the question, and it goes back to Reagan's question, which is an extremely, very, very thoughtful question. In the fact is, can we just multiply or divide by 6 on the moon? Well, we have a problem with certain equations. So if I have a dropped ball, right? If I have a dropped ball on Earth, here's the ball. I'm going to drop it, and I want to know its final velocity, right? So if I said I'm going to drop it, it's 100 meters. No air resistance, 100 meters. How fast is it going when it gets to the bottom? Well, that's pretty straightforward. Vf squared equals Vi squared plus 2As. So Vf squared equals 0. I'm dropping it. I'm going to make it really simple. Drop it plus 2 times negative 9.8 times 100. So my final velocity, if we were to work that out, what was that, 1960, square root of that, 44.3? Okay, anybody have a question on that? If I'm just dropping a ball on Earth, no air resistance, 100 meters, it's just going to fall and end up at 44.3 meters per second. Yes, ma'am.
Sometimes I get confused on like which one needs to be equal to 0.
Oh, okay. Dropped, your initial is 0, because it's going to accelerate and be final velocity. If you throw it up in the air, final is 0, because you got to think, when it gets to the top, it stops going up and comes back down. Always, ask. Those are the types of questions that we've got to keep asking, because that's going to become part of even the next thing we're doing is when we add horizontal and vertical together into one thing called parabolic motion or projectile motion, which you've done in math, but we'll actually do it in here and trying to figure out how to separate those two pieces. Yes, ma'am.
You just said if it's dropped, the initial 0,
Uh-huh.
and then if it's thrown, the final 0.
But just think about it. 0, right? 0, final velocity is something. Here, when I let it go, and then at the top, 0. So you got to think about the physicality of it. It's one of the things about physics. If you think about the physicality, and it's the funniest thing. I was taking a test in college with Xing Quan and Bill Fast and Stuart Erickson and Rick. Yeah. Rick didn't do this. The 3 of us did, or the 4 of us did this. We're sitting there going, and it was electronics, and we were going. Because there's something called a right-hand rule, right? Right? If the motion of the wire is this, and the electricity is going that way, the magnetic field goes this way. So we're going, but we had to turn our hands over because it was, oh, wow, okay, so the magnetic field's going that way, the current's going that way, so the force is going that way. So we're all doing the same thing. We're all doing these hand gestures of like, okay, so left hand for right hand, so right hand. And we're all doing that. So I look around, and it's just absolutely hilarious. We're going, and Rick's over there just, he just knew his stuff. So, yes?
On that, wouldn't you have to like square root a negative if you did that?
No, because this is actually going negative, because it's going down.
Okay, so would it be like a negative 100?
Right, so this is a negative 100 here. So you could either do a negative velocity, or if you have a negative distance, yeah. So you have to work with your negatives to make sure they're correct. All right, so let's go to the moon, right? So same situation here, drops down, VF. So what changes? Well, I still have my VF squared equals VI squared plus 2AS. So what's your prediction? Do we divide or multiply by 6? Well, let's take a look. VF squared equals 0 plus 2 times 9.8 divided by 6, distance S. So VF squared is equal to, and that S is 100. And so if we multiply that out, 9.8 divided by 3 times 100, it's 327, and I take the square root of that. Doesn't work.
Doesn't
It's not 6 times. Because of that square.
So it should be 6 times. You should be able to say 18.1 times 6, and it should give you.
Should be that, if it was truly. So that's what I'm saying. It doesn't work in every case to just multiply or divide by 6. Yes, ma'am.
So if you wanted us to solve this, what would the question look like?
Okay. On the moon, I drop a ball off of a 100-foot cliff on the moon. How fast is it going when it gets to the bottom?
Okay.
And then compare that to the same situation on Earth.
Gotcha. So you're not going to give us like 58, we're going to give us any numbers to solve.
No, a lot of those are theoretical questions. I'd rather try to make it more real, right? So that's kind of where we're stuck. So anybody actually divide that out, find out what that was? Because I'm always curious about numbers. 2.44 doesn't seem like it's something that you could hang on to. Yes.
So if you can't divide by 6, how do you figure it out? I think there's
Okay, I can't just take this number and divide it by 6. I can when I throw it up into the air because the v squared is here. I'm not taking a square root for my answer. This is 0, so the one we did before, that was 0 and that was 22. So I'm solving for this. I'm not taking a square root. But if I'm taking a square root, these aren't going to be just by 6. So what we do is we just divide the acceleration by 6 and solve it normally.
so this one's right.
Yep, that's correct. I just can't divide the answer by 6. Yes, ma'am.
So 2.44 is actually the square root of 6. So if I
2.44 is the square root of 6. There's the connection, but that doesn't make sense since we're taking the square root. It's the square root of the variable we're looking at. If you want to remember that, have a good time. I work it out, right? Same way, but that is a cool connection. Thank you for telling me that because that is the 2.44 squared is 6. And it's because you're taking the square root here that we don't have a difference of 6 times. Right? All right. I would like to do number 45. I actually want to go back to the other page and take a look at number 45. All right. I want you to try to do this. Okay? And before you start trying, I want to give you a hint. This is the bowling alley turned this way. The bowling alley, remember you let go of the ball and then you hear the time of the bowling pin and the bowling ball hit a certain amount of time later. This is exactly the same thing except you're dropping it off a cliff. And you're hearing it a certain time later. So you should be able to, in your notes, find that bowling ball problem, and you can solve this the same way. All right, so we're going to have the rest of the period, and then we're going to open up with that tomorrow, and then continue on doing a couple of problems.